And today we will continue looking at different ways to visualize data using Pandas and Matplotlib. I guess in the last few minutes of the last class, we began lesson 2. We only got to the point of our import statements. We have NumPy, Pandas, and from Matplotlib import pyplot, and Matplotlib inlines. And I think I said this last time, it's good habit to have all your import statements at the top of your notebook, because then if you share this notebook with someone else, they can see immediately what libraries you're using. So let me re-execute this one by one. Reminder that this pyplot_rc command allows us to change the default value of some plot settings, and you should certainly look at the documentation page about this to learn different things that you might want to set for your plots. Here again, Beers is going to be a Pandas data frame that is created from reading our comma-separated values file, and we looked at the first few lines here. Just that always helps us to see the structure of the data. We see the names of the columns, which we can use to access the data of the column, to extract the data of the columns into a series, for example, to do some things as we've done before. We saw that there was 2,400 lines, and we were starting the discussion about quantitative versus categorical data at the end of last class. By the way, we haven't talked about this IBU feature of the Beers. It's called International Bittering Unit, and it measures the parts per million of a particular component that is an acid found in hops. So that also, you can find that little bit of trivia if you read the lessons, the written lessons. And we were up to now working with the ABV and IBU columns because they contain numeric data. So we could get the central tendency of the data via the mean. We can get the distribution of the data graphically using a histogram, but also quantitatively using the variance and the standard deviation. Don't forget that for standard deviation and variance, there is a technical difference between analyzing a set that contains a whole population and analyzing a data set that contains a sample. And I recommended highly a video on YouTube. It's a technicality, but it's important because it changes a little bit the result numerically. That difference in the formula will perhaps make the result wrong. Wrong in the numeric sense, it's like close, but not exactly the same. And so if you compare with Python two results and they vary in the last decimal place, they're not the same numbers. So if you have that, remember always to check. I wonder if I should have used something different here for sample instead of population variance. Okay, that was the ways that we study quantitative data, but there's another kind of data we call categorical, and that would correspond to something like the style, where we don't have a number, we have something different. So we've got the data in a data frame. So let's repeat the steps to extract the series and clean the data. So let's just say here, repeat the cleaning of data. And for ABV series, that was the name of the variable we chose to get from the Beers data frame, just one column, which has the label ABV. Okay, so that gives me the series, but that series has a lot of missing values. So we create another series. That's right. Another series, but only with the numeric value. So we take ABV series and we apply drop NA to remove the missing values. And the other thing that we did is take the values of just the column. Remember, a series is the column plus the row indices. So we can extract just the values of the column using the dot values property of the series. That will repeat the process we did for the ABV column, which is alcohol by volume of our Beers data set. And let's do it again now for IBU. IBU series is Beers column IBU. IBU clean is IBU series, but without the missing pesky nans. And IBU is IBU clean dot values. We extract the values into a NumPy array. So type IBU, that is a NumPy array. Now, we learned in the previous lesson to make a histogram using NumPy by grabbing this IBU NumPy array. But it turns out that Pandas has a simplified way to plot a histogram directly on the series. And so let me turn that into a markdown cell. I'm actually going to add a couple of cells there so I can scroll up a little bit. And I'm going to write here Pandas. I'm going to use 2 asterisks to get a bold. Now, it really is Matplotlib under the hood, but Pandas has a different syntax, and the syntax is simply you use the data frame name. I'm just going to call it data frame. That represents the variable name of the data frame, and you do .hist for histogram, and then as argument you pass column and equals and the label of the column. So now that simplifies and saves you some steps. So for example, if we wanted to plot the beers column, let's go back here. There it is. That's the column, the ABV column. But now I'm saying we can access that directly from the data frame, which means I didn't even have to extract the series. And I could have done beers. That's the data frame. And I can say .hist and indicate what column I want to plot, ABV. And I can skip all of the previous steps of extracting the series and removing the nans and all of that. One thing I'm going to add is an optional command to get the edge color to be white. And all this does is it allows me to see the columns much better. Let's also add a title because of course we like our plots to be complete. And because the pandas.hist plotting method is accessing Matplotlib under the hood, I can still apply pyplot commands to fix my plot like I want it. So pyplot.title, say alcohol by volume of the beers, and shift enter to execute. And there you have it. I have a histogram with just 2 lines of code, which is very nice. It's convenient. I have to type less. If you do the plot with Matplotlib, you have maybe a lot more fine-grained control and you can make it just so. So really the application will dictate which one you choose. This is just another possibility. Many times with Pandas, you will start with this because it's faster and more concise. But as you get more advanced or you want something that is very special, then you'll start using more, perhaps, the Matplotlib version. So it depends on the situation and it depends on your preference. And similarly to that, we can learn as well that, remember that last lesson we were using numpy.mean to compute the mean value of an array, but we wrote our own custom functions to compute the variance and the standard deviation. NumPy, of course, has built-in functions to do that, so we really didn't have to. So let's leave another note here to highlight that NumPy computes variance and standard deviation. So we're learning some pro tips here, and it won't surprise you that the syntax is you put the array as a variable name and bar for variance. Now, one thing that is interesting, so let me just leave it here for a moment. And I have pulled up the lesson. Okay, so this is the second lesson of our module. And let me go down to where we present the NumPy version. Here it is of these commands. I want to point out, and I want to highlight again, that in the written lessons, we often have a link when we introduce a new function to the documentation. Of course, you can always Google it and you will find it. But here's documentation of the variance. So let me make that a little larger so you can see. Oh, it tells me that I am pointing to an old version of the documentation because new versions of the software are released every so often. Hopefully it hasn't changed very much, but for now, let me just read it from here. So I want to note a couple of things. Okay, there are some optional parameters in the function. This is technically the word that people use in Python and in computer science in general. This is the signature of the function. The signature means what is the interface like, what types of parameters it expects. As you can see, only A doesn't have the equal sign here, right? The equal sign, whenever you see that, the equal sign here in the, let me make that a little larger. in the signature of the function indicates that this parameter is optional. And if you don't give this parameter to the function, then the value that it takes is that default value, none. Okay. But A doesn't have that equal sign. So A is required. So the minimum thing that you need to pass is an array to take the variance of that array. But then access, for example, would allow you to decide, as you can see here, along which axis you compute the variance. The case could be that you have a multi-dimensional array. In the case of a one-dimensional array, it's obvious that you only have one axis. Now, I want to highlight that there is another optional parameter here that's called DDOF. Now, if you watched the recommended video about sample and population variance from Professor Sainani, you would have heard her say that when you're working with a sample, it's like losing a degree of freedom. And that's technically how people in statistics talk about that. So this DDOF has to do with that degree of freedom. And if I scroll down to what this is, the technical word from statistics is delta degrees of freedom. That's the technical word. So DDOF. And it says here that this is the divisor, they mean denominator, used in the calculation, of what? Of the variance, is n minus DDOF, where n represents the number of elements. So n minus 0 means that I'm dividing by 1 over n. If you recall from our lesson, that is for population. If I'm computing the variance of a sample, then the denominator is n minus 1. And so I have to give it DDOF equals 1 in the NumPy function for variance to achieve that. Okay, so this is something to pay attention to. So I'm going to go back to my notes here, and I'm going to add here this array. I'm just going to call it X. Let's call it X. And then we want to have this DDOF equals 1. And I'm going to say here for sample variance. And then I'm going to use in parentheses, I'm going to say use DDOF equals 0 for population. That's how I'm going to write my notes to self and modeling how you might take your own notes using Jupyter. So if we wanted to compute the variance, for example, of the ABV column, we could say, okay, I'm going to save that into var ABV. That's a new Python variable that I'm going to obtain from doing NumPy. So I guess I should have written this differently here to not confuse things. It's numpy.var, and I am confusing things in my presentation here. Numpy.var, and the array goes in there. Now that makes sense. Numpy.var, array, degrees of freedom. Okay, so what is the array? ABV is the array. And like I said in the beginning of this module, we have to assume that the Beers dataset is a sample, because it would be like improbable that it contains all of the possible beers in the world. And so we have to assume sample here. DDOF has to be equal 1 to get a sample variance. So let's print that. Let me compare when we computed that with our own function from the previous lesson. So let me add here a line and say sample variance, and it must be ABV. And I see here an output, 3 zeros and 1 0 ending in 6-2. Let me compare with today. And you can see that the beginning, 3 zeros and 18, those numbers are the same, but you can see that it's different in the last few decimal places. So it's a small, tiny difference in the way that the NumPy function computes the result that I obtain, but it's literally the last decimal place. And DDOF equals 1 is probably always going to be the case that you use that, because we're dealing with samples. We're always dealing with samples, hardly ever dealing with a population. All right, so NumPy syntax for computing variance and standard deviation. And it saves us a lot of work. And of course, we can compute the standard deviation from taking the square root of that. The standard deviation is the square root. So I could just do NumPy. Let me save it into a Python variable and say standard deviation of ABV is, and I'm going to do NumPy.square root of the variance, which I already saved into a Python variable. And let's print it. And we now can compare. We can compare now with the results that we obtained with our own function. For the standard deviation, up to 3 decimal places for ABV is 0.014. And we had a very good question last time about whether the print statement was rounding or not. And indeed, we learned that it is rounding. So it is the same result, but it's just rounded in the other display. Okay, but of course, you might be wondering if there is a numpy.stt function to do the standard deviation. And yes, there is. So we could find out by using the question mark and shift enter. This pulls up the manual page of the standard deviation function from the NumPy library. Notice that it says at the very top, signature. That's what I was referring to earlier. That's jargon, really, to refer to the way the function is used and the list of parameters that it takes with their default values, if there are any. And then the instructions here are the same ones that you would find in the online documentation for NumPy. So those are the NumPy functions to compute standard deviation and variance. Let me reiterate the importance of taking the time to read these documentation pages. Whenever you're learning new functions, do take the time to have a look at these. Sometimes they're a little difficult to read. They have a lot of information, but over time you get better. You recognize the patterns and it becomes a skill to read these documentations, and it helps you to learn new things because, for example, at the bottom of this page, I have a list of other related functions. And by reading this, you can start learning more. There's even an explanation here about the meaning of this degree of freedom argument. So do take the time to read these pages. Okay, so what we're going to do next is learn a few other things that we can compute for quantitative data. All of these things are for quantitative data. And so I'm going to go back here and add like a subheading here first. We're working here first with quantitative, ABV and IBU. We're still doing quantitative data. So one thing we haven't learned about is the median. The median value, and let me write that here, it essentially is the value of in the data that cuts the data in half. You have half of the data points are smaller and half of the data points are larger than this one, this specific data point. And if you have an even number of data points, then you take the average of those two in the middle. So the median essentially cuts your data set in half. It's the middle data point. Often when you're looking at the data set, you want to know things like where's the center? How is the data distributed? And the median is another way to indicate the center of the data. It tells you something about that shape of the data set. And of course, we can compute it with NumPy. And NumPy has this built-in function. I'm going to write it right here. Syntax NumPy.median, as you would expect. And so let's compute the median. Let me pause for a moment and ask you to apply NumPy.median to the IBU and ABV values. So I can take a breath. Okay, so the median is another one that we have. And now let me show you some other way to look at the data, which is called a box plot. And this represents what I was telling you earlier, that you always want to visualize. This is another way to visualize the distribution. And what we mean by distribution is like the shape of the data. We're interested always in the shape and also the characteristic, like where is the center and so on. And the box plot, let's apply it right away. pyplot.box, not too surprisingly. And how does it work? We pass it an array and we can add an optional argument, which is the labels. And it's a plural labels because you can plot more than one array with this command. And then you would have a list of labels corresponding to each array you're plotting. So this is where it's important to read documentation. This is only one array that we're plotting, and I'm going to add the semicolon. Oops. Oh, it's box plot. Okay, there we have it. Box plot. All right, so what is this? Here's the box plot. One array and only one item in the list of labels because I'm only plotting one. Okay, so let me annotate this. Maybe I could use a little arrow here. Yep, there. Slightly higher up to my arrow, you see that there's an orange line, hopefully. That orange line corresponds to the median. Look at that. Okay, that's the median. You see, of course, there's a box. So at the bottom of the box is what we call the 25th percentile. And what is a percentile? The nth percentile means that below that data point lies n% of the data. So 25th percentile means that below that value, 25% of the data points fall. This one at the top is the 75th percentile. Thinking about this, the median, remember the median divides the data in half. So it means that 50% of the data lies below it. So the median is the same as the 50th percentile. Okay. So this one below is the 25th percentile, and the line above is the 75th percentile. This one right here is the 75th percentile. And then it has these two lines, which are called the whiskers of the box plot. These are an indication of how much more scatter there is in the data. But of course, the middle of the box contains, if it's between the 25th percentile and the 75th percentile, it means that half of all the data points lie in the box. Half of all the data points lie in the box. And the whiskers are computed in a funny way. Okay, so to learn about the whiskers, I have to first introduce the idea of interquartile range. The interquartile range is the height of the box, which is between the 25th and 75th percentile. So let me just write that here as a note. The size of the box is the difference between the 75th percentile and the 25th percentile. This is called the interquartile length, because the 50th and 75th percentile are called quartiles. So let me add that. The 25th, 50th, and 75th percentiles are also called quartiles because they all divide the data in quarters. Okay, so this is a little bit of concepts from statistics. You probably learn more about this in your class that covers statistics and probability later on in your engineering career. But in NumPy, we can compute percentiles. We have a function that computes the percentiles. So let's learn about that. NumPy computes percentiles. And how does it do it? Well, we give it so let's write the syntax again. We give it the array and we give it the value here of it has a Q, but you can give it any value for in this case would be the 25th percentile. So you change the value that you give it there according to so for example, let's compute the quartiles for ABV. So I'm going to compute Q1 ABV, and that's going to be numpy.percentile and ABV, and Q equals 25. That's the first quartile. Q2 ABV, I get it with, that would be the median, which corresponds to the 50th percentile. And I wanted to do one more, but I executed instead. So let me do one more, which is numpy.percentile with ABV, and Q now is 75. And I'm computing them because now we can use them to get the whiskers. So the whiskers of the box. Now I'm going to compute them and see if they make sense with what I'm seeing in the graph here. Okay, so the whiskers of the box plot, the top whisker is computed as follows. It is the lower value of either the maximum. I'm just going to write max, and the Q3 plus 1.5 times the IQR, where IQR is the interquartile length. I'm going to add it up here for completion. And then the bottom whisker is the higher value between the min and Q1 minus 1.5 times the interquartile range. And let's see. So I guess I could use the Python version of multiplication here instead of an X, which would be confusing. Let's do it that way. And that is just a decision from the designer of the box plots. And so let's compute. Actually, we do have this as an exercise, and I'm going to paste it here as an exercise and give you a few minutes so that I can take a breath. Go back, copy that, paste it there, and I'm going to take the camera off so you can read it and get a couple of minutes. calculate the endpoints of the top and bottom whiskers, just the ABV because we didn't compute IBU. Okay, a couple of minutes there for you to work on your own, and hopefully you computed the top and bottom whiskers. And this is a little bit tricky because you have to think here, okay, is the lower value between the maximum. So what it's saying here is the top whisker, it's either the value of the maximum data or this here calculation is something above Q3, obviously, because Q3 is the top of the box, right? And that which is above Q3 is 1.5, the height of the box. And the idea here is that every data point that is beyond the whisker can be considered like an outlier, like it's far from the central area of the data. And so here you see that there's only one data point below the bottom whisker. And so that data point is probably, it's actually weird because if you look at it and I read it, it says 0. So they have a beer that has 0 alcohol, and that is certainly an outlier in this data set. On the other end of the scale, there are quite a few, in fact, that have higher values. So that's the idea. This box plot is used very commonly in statistical analysis, and people get very good at interpreting them in terms of what it means for the shape of the data set that you're looking at. You should definitely try to do it yourself and understand it. Let me go back here to this part of the notebook, the lesson, to share this little bit of history about the inventor of the box plots, which used to be called box and whiskers plots. The inventor is a man named John Tukey. I guess it's pronounced Tukey. And he was a famous mathematician, and he is said to have invented the word software. And he was part of the people working to break the Enigma code in World War II. Worked at Bell Labs, and it was a very oh, and look, I just found a typo in my notes that have been there for quite a while. And he did some very interesting work in statistics and is credited with having been the person who consulted for the educational testing service, for example, for things like how to do, well, the testings, the SATs and things like that, all the testings that we live with today. He was the consultant to those organizations and also the Census Bureau and so on. So a very famous statistician of the wartime. And another note, sometimes you'll see the box plots drawn horizontally. And if you have several data sets that are drawn together, then you can compare them in terms of their distribution. So they're very much used in empirical sciences. Okay, so that's the end of the part of the additional work on quantitative data. Now we're going to talk about categorical data. And the categorical data that we have in this data set, beers, we have the name, of course, and we have the style. The style seems more interesting than the name. And a typical way, just like we have histograms for quantitative data, the typical way to visualize categorical data is bar plots. And what is the idea of the bar plot? They will show visually the number of times that a particular category appears. For example, in our data, the American IPA, how many beers are in that category? That would be a typical question you would ask. And we haven't done anything with the style. So let's first get let me go back and look again at the label for that column. It's just called style. And so I'm going to use the label to extract that column into a series. I'm going to call it style series because that is a variable name that is readable to a human. And it's coming from the beers data set and from the column that has the label style. Okay, so let's double check always our sanity checks with the type. It's a pandas series, which means the column of data with the row indices together. So if I wanted to look at, for example, the first 5 entries, we could do that style series and grab a slice and look at that. And you have, those are the first 5 items in the series. And you can now Observe that the row index is part of this variable. It's not just the data. It's the data and the row index. And already in the first 5 items, I see that American IPA repeats. And so we have 2 beers of that same style. So we can ask ourselves how many items are of each style are contained in the whole data set. That is the first question that we may ask. How many beers are there of each style? And fortunately, Pandas has a built-in method to give us that, to answer that question, and it is value counts. So if I were to do style series, that's the series, dot value counts, this is going to give me the frequency where each one of these things appears. But I don't want to just print it. I want to save the result to another Python variable. I'm going to call it style counts. Okay. I'm going to save the result of applying that method into a new Python variable. I don't see any output because the important thing that happened there is the assignment. So let me ask Python again, what is the type of style counts? And observe that this is also a series. So it's not just an array of numbers, it is also a series. Why? Because look, style counts. Let me show a slice of the first 5 rows. I need to have 2 things, the name of the style and the number of times that it appears in the data set. So it is a series where now this is interesting. Remember that we could do always the dot index, style counts dot index. The dot index now, and this is a bit messy because it's a bit long, but the dot index is now the name of the style. So the name of the style American IPA has a frequency of appearance in my data set of 425 times. The important data here is the counts, 425, and the name of the beer, the name of the style became the label of the row. Okay, I'm going to cut that out because it's a little messy, but it was a way to show you that here, this label, the style now is listed here, but it is in fact has the role of a label in that series. Let me do len style counts. I inadvertently used the keyboard shortcut to get line numbers there. That's why the 1 appeared here, by the way, because you can always get line numbers on your code cells. 99 styles, different styles. And the len function now is telling me the number of rows in the series. Okay, so there are a total of 99 styles in our beers dataset, which I think is quite a lot. I never imagined that there would be so many styles of beer. And so it's important to notice here that value counts returned a series. Okay, here it is, a Pandas series. And another thing to notice is that it is sorted. At the top row is the beer that is most popular in our data set. So the next most popular, 245, a long way off, is American Pale Ale. Then what we can do is the final thing that we can do is get the bar plot of those styles. If I do style counts, and I do a dot plot, bar H is the horizontal bar. And I could give it various things like a figure size inside. Let me start with that. And you'll see that when I do that, it's horrible. Okay, horrible. Why? Because we have 99 different beers. And you try to put the labels. We already decided that we were going to use over here at the top, where is it? A rather large font size. So with that large font size and 99 different beers, this is a mess, right? So what we can do is slice our series. And I have to do the slice right here before the dot plot to get, for example, I'm going to do 0 to 15. Now I get something more readable. It's still a bit large. My font size is a bit large. Maybe let's see what happens if I just change it up here. And now I'm going to re-execute that. I'm going to add a colon at the end to suppress the Matplotlib. Okay, this is looking a little bit better, right? Another thing that we can do is we can change the size here. We can do a fixed size and change that to So this is width and height. 10, 8. Let's see what that does. And now I can get that little extra space between the bars because I stretched it out vertically a little bit more, and that works better with my font size. I don't want to make the font size too small because maybe I'm going to share this report, print it out, and share it with people whose eyesight is not so good. So I want a nice readable font size, but I can fix my problem in the plot by making it taller. Other things you can do is you can add a color, you can add the edge color, and various things like that if you want. But that, I think that bar plot already looks pretty good. And we can probably leave it there.